Electric cars were supposed to be simple. Fewer moving parts, higher efficiency, a clean break from a century of mechanical complexity. But something doesn't add up, because modern EVs are carrying their own weight twice. A massive battery, already the heaviest component in the car, is being treated like fragile cargo, wrapped in layers of structure, reinforced, protected, and then surrounded by another structure, two systems, doing almost the same job, which raises a dangerous question, not about batteries, but about the way we design cars. What if electric vehicles were never supposed to be built like this in the first place? Electric vehicles were never meant to look like this, not in the beginning. Long before lithium-ion batteries, long before software-defined platforms, cars were built around a very simple idea. Energy and structure were separate. In an internal combustion vehicle, fuel was just fuel. A liquid stored in a thin-walled tank. It didn't carry load. It didn't reinforce the chassis. It didn't matter structurally. The real strength of the car came from somewhere else. A rigid frame, a unibody shell, a carefully engineered structure designed to handle forces, torsion, bending, impact. Two completely different systems. One stored energy. The other carried the car. And for over a century, this separation made perfect sense, because fuel was light, temporary. It burned away as you drove. Then electric vehicles arrived, and suddenly, everything changed, because the energy source was no longer light. It was heavy, extremely heavy. A modern EV battery pack can weigh hundreds of kilograms, sometimes more than 25% of the entire vehicle mass, which creates a strange situation. The most important component in the car is also the heaviest. So engineers did what the industry always does. They adapted the old idea. They took the battery and placed it inside the existing structural philosophy, protected it, reinforced it, built a frame around it. And eventually, this evolved into something we now recognize instantly. The skateboard platform. A flat battery pack mounted low in the chassis, with motors and suspension attached around it. At first, it looked like the perfect solution. Low center of gravity, better handling, simplified packaging. And for a while, it worked. But hidden inside this design was a quiet inefficiency, one that most people never noticed. Because even though the battery sat at the bottom of the car, it still wasn't part of the structure. It was still being treated like cargo. Valuable cargo, dangerous cargo, but cargo nonetheless, which meant something subtle but critical. The car still needed a full structural system, separate from the battery. A frame, reinforcements, crash structures, all built around the heaviest component. And this is where the contradiction begins. Because now the vehicle has two overlapping responsibilities. One system designed to carry loads, another system carrying weight, but never truly working together. So the question becomes unavoidable. Not about performance, not about range, but about architecture. Why are electric cars still designed like machines that were never meant to carry batteries in the first place? And more importantly, what happens when that assumption is removed? The problem with modern electric vehicles is not the motor, it's not the software, it's not even the battery chemistry. It's something far less visible, the architecture itself. The physics problem. At its core, every vehicle is fighting the same enemy, mass. The heavier the car, the more energy it needs to move. The more energy it consumes, the shorter its range. It's a simple relationship, almost unavoidable. But in electric vehicles, this problem is amplified. Because unlike fuel, which gets lighter as it burns, a battery never loses weight. It carries the full burden, from the first kilometer to the last. Now consider this. The battery is already the heaviest component in the vehicle, and yet it's not contributing to the structural strength. It's just sitting there, which creates a fundamental inefficiency. A massive object that adds weight but not function. And this is where things start to break down, because engineers now have to compensate. They must design a separate structure strong enough to carry the battery, instead of letting the battery carry itself. The legacy solution. So how does the industry solve this? By adding more structure, reinforced frames, protective casings, crash barriers, layer upon layer of engineering, all designed to protect the battery from forces that the structure itself is supposed to handle. In a traditional EV platform, the chassis handles loads. The battery is protected inside. The two systems are mechanically separate, which sounds safe, and in many ways, it is. But safety comes at a cost, because every layer added adds weight, and every kilogram added reduces efficiency. This creates a paradox. To protect the battery, you make the car heavier, but making the car heavier means you need a larger battery, which makes the car heavier again. A cycle, difficult to escape. The hidden inefficiency. This is where the real problem reveals itself. Modern EVs are not just heavy. They are structurally redundant. Think about it. There is a structure designed to carry loads, and inside it, another component that could potentially carry loads, but isn't allowed to. Two systems, doing similar jobs, but never integrated. This leads to three major consequences. First, weight penalty. The vehicle carries unnecessary structural mass, which directly impacts energy consumption, acceleration range. Second, complexity. More parts, more connections, more failure points. The system becomes harder to optimize and harder to manufacture. Third, cost. Every additional structural element requires material, requires assembly, requires validation, which increases production cost significantly. And yet, the industry continues to build cars this way. Why? Because this is how cars have always been built. Structure first, everything else inside. But electric vehicles were never supposed to follow that rule. They introduced a completely different constraint, a heavy, rigid, energy-dense component, sitting at the center of the vehicle. And this is where the story becomes interesting, because once you see the problem clearly, the solution becomes almost obvious. What if the battery was never meant to be protected by the structure, but to become the structure itself? And this is where everything begins to shift, because instead of asking, how do we protect the battery? A different question emerges, one that challenges the foundation of automotive design. What if the battery doesn't need protection at all? What if it is the structure? This idea leads to something radically different, a concept known as the structural battery, a different way of thinking. In a traditional vehicle, structure is something you build first, a rigid skeleton. Everything else, engine, fuel, passengers, exists inside it. But a structural battery flips that idea completely. Instead of building a car around the battery, you build the car from the battery. The battery is no longer an isolated component. It becomes a load-bearing element, a core part of the vehicle's architecture, which means it now does two things at once. Stores energy, carries mechanical loads, and that changes everything. The architecture, from pack to body. To understand this, it helps to look at how battery design has evolved. First came cell to module, small cells grouped into modules, modules assembled into a pack, structured, replaceable, but heavy. Then came cell to pack, modules removed, cells integrated directly into the pack, fewer parts, higher energy density. And now we arrive at the next step, cell to body. Here, the battery pack is no longer a separate unit. It is integrated directly into the vehicle's structure. The floor of the car is the battery. The chassis depends on it, which means something profound. Remove the battery, and the car no longer has structural integrity. Engineering breakdown. So how does this actually work? How can a battery carry loads? The answer lies in how forces move through a structure. In any vehicle, forces travel along specific paths, from suspension to into the chassis to across the body. These are called load paths. In a structural battery system, these load paths are redesigned. Instead of bypassing the battery, they go through it. The battery casing becomes rigid. Cells are bonded together, often with structural adhesives. The entire pack behaves like a solid panel. This creates something engineers care deeply about: torsional rigidity. A stiffer structure means better handling, more predictable dynamics, improved safety. And here's the surprising part: because the battery is already large and flat, it's actually an ideal structural element, like a giant shear panel. So instead of adding structure, engineers are removing it. The benefits: once the battery becomes structural, several things happen at once. Weight drops, because redundant chassis elements are eliminated. The battery is doing double duty. Efficiency improves. Less mass means less energy required, which directly increases range. Manufacturing simplifies. Fewer parts, fewer welds, fewer assembly steps. This is where it connects to another transformation: large-scale casting. Entire sections of the car produced as single pieces, integrated with the structural battery, and suddenly the vehicle becomes something else entirely. Not a collection of parts, but a unified system. The paradox. But this approach introduces a new challenge, one that feels almost contradictory, because the battery is now the most critical energy component and the main structural element, which raises an uncomfortable question. What happens in a crash? In traditional vehicles, structure absorbs impact. Critical components are protected. But here, the thing you must protect is also the thing absorbing the force. This creates a new kind of engineering tension, one that forces a complete rethink of crash structures, material design, repairability. And this is where the industry begins to divide. Some manufacturers are pushing aggressively toward this future. Others are more cautious, because adopting structural batteries is not just a component change. It's a redesign of the entire vehicle philosophy. And that leads to the final question. If the battery can replace the structure, then what happens to everything built before it? The shift towards structural batteries is not just a technical evolution, it's a philosophical divide. On one side, traditional automakers, companies that have spent decades perfecting the art of building cars around structure. Rigid platforms, layered safety systems, separation between components. For them, the idea of turning the battery into a structural element introduces risk. Not just engineering risk, but manufacturing risk, repair risk, regulatory uncertainty. So their approach remains cautious. Incremental improvements, cell-to-pack, reinforced skateboard platforms, optimizing within the existing framework. On the other side, new entrants, companies that were never bound by legacy architecture. For them, the question is different. Not how do we improve the car, but why is the car built this way at all? And this is where the divergence becomes clear. Instead of adapting the battery to the car, they redesign the car around the battery. The result is not just a lighter vehicle, but a simpler one. Fewer parts, fewer interfaces, fewer compromises. But simplicity comes with trade-offs. A structural battery is harder to repair. Damage to the pack can mean damage to the entire vehicle, which raises a critical question. Is this the future of automotive design or a high-risk shortcut? Because if this approach succeeds, it doesn't just improve electric vehicles, it makes an entire century of car design obsolete. For over 100 years, cars have followed the same fundamental rule. Build a structure first, then place everything inside it. Engines, fuel, passengers, all treated as contents, carried by something else. Electric vehicles were supposed to break that pattern, but for the most part, they didn't. They simply replaced the engine with a battery, while keeping the same underlying philosophy. And now, that assumption is finally being challenged, because the moment the battery becomes structural, the car is no longer assembled, it's integrated, no longer a machine made of separate systems, but a single, unified object, where energy and structure are no longer divided. And that changes the question entirely. The future of automotive design may not be about better batteries or faster motors, but about something far more fundamental, rethinking what a car actually is. Because in the end, the biggest innovation in electric vehicles may not be electric at all. It may be architectural. And once that shift happens, there is no going back.